All right, so I'm going to go through this kind of quickly. We still have class that we can get any questions or anything. And we kind of gone through this quite a bit. But remember, for questions 1 through 7, you'll only be able to use your iPad as your calculator, not an actual calculator, because for the square root questions, it'll do it for you. But what we're trying to do is if I give you the square root of 4, well, you should know that that is equal to 2. If I give you the square root of 9, you know that that is equal to 3. Square root of 16 is equal to 4. And these are all called perfect squares because it's numbers that we can take the square root of. So when we're simplifying radicals, regardless if it's a square root, cubed root, fourth root, we're trying to see are there any numbers that are perfect squares that we can take out of it. So we're trying to lower the number inside the radical as much as we possibly can to where there's nothing that can be taken out. So if I give you 18 over 12 and I ask you to simplify this fraction, well, they're both divisible by 6. So we can rewrite this as 3 times 6 over 2 times 6. And we can think of this as we're multiplying and dividing by the same number so they can cancel each other out. And we're just left with 3 over 2. So you see there, like we're looking to see what operations are being done to both the numerator and denominator. And then we're taking that out so that we can rewrite it in its simplest form. So same thing happens with these radicals. So you can use your cheat sheet, and the first thing we do is say, well, what perfect square goes into 675? And you can test these perfect squares, like just go down your list. 25 does go into it, and we know that's a perfect square, but so does 225. And whenever more than one perfect square goes into it, we want to take the largest one, just so that way we don't have to do this multiple times. But as we talked about in class, you can take, if you can identify any perfect square that goes into it, then go ahead and do that one right away. And then from there, you just might have to do it a second time. But 225 goes into 675 three times. So I can rewrite, since 675 is equal to 225 times 3, everywhere I see 675, I can rewrite it as 225 times 3. So I can rewrite this as 225 times 3 underneath of this radical. And now what I'm going to do, and you don't have to do this step, I'm going to separate these and look at them as their own number. So I'm going to rewrite it as the square root of 205 times the square root of 3. And the square root of 225 is 15. So this can then be rewritten as 15. I can't take the square root of 3 without it being a decimal. So and there's nothing else I can take out of it. So that means it's 15 times the square root of 3. So you see what we're doing is we're taking out any number that is a perfect square that's embedded within this, and we're just removing it so we can write the number that's inside the radical that's left over in its smallest number possible. All right, for number 2, I'm going to go ahead and do this one a couple different ways just to show you what I was talking about, that if the first number doesn't jump out at you, of what the smallest one is or biggest one is, that you can still do it by the smallest one. So when I see 72, I know that 9 goes into it. So maybe right away I'm just like, okay, I'm just want to get some of these numbers down. So 72 times 9, I'm sorry, 8 times 9 gives me 72. So everywhere I see 72, I can rewrite it as 8 times 9. So I can rewrite this as 8 times 9. And I'm going to just go ahead and separate this to say the square root of 8 times the square root of 9. And I know the square root of 9 is 3, so then I can rewrite this as 3 times the square root of 8. But just because I take something out once doesn't mean I'm done. Like with that 18 over 12, if I divided both of these by 2, I would get 9 over 6, but 9 over 6 can still be simplified, so I had to keep going. And at this point, oh, I see 8. Well, I know 4 goes into 8. 8 is equal to 4 times 2. So now this can be rewritten as 3 times the square root of 4 times 2. And then I can go ahead and rewrite it. I'll do it up here as 3 times the square root of 4 times the square root of 2. I can separate it. You don't have to do this step. And the square root of 4 is 2. So now it becomes 3 times 2 times the square root of 2. And 3 times 2 is 6. So 6 times the square root of 2. So you see, even if the largest number doesn't jump out at you, if you know 1 goes into it, simplify it. And then it gives you another smaller number that you might be able to identify quickly that another perfect square goes into it. I'm just going to erase this real quick and do this one with the largest number. All right, so 36 goes into 72, and 72 is equal to 36 times 2. So I can rewrite 72 as 36 times 2, because I know that they're equal to each other. And then I'm going to separate them and look at them on their own. So 36, the square root of 36 times the square root of 2, and the square root of 36 is 6. So times the square root of 2, because I can't reduce that. So you see, if you know the largest one, go ahead and do it. If you don't, just do the one that you see that you know goes into it, and then just look and see, well, does anyone else go into it as well? Some people find that way to be easier because there's less thinking or less dividing that you need to do. Whereas some people just want to get it done with in one step. So then they like to go through and find that largest one. All right, now there's a difference between number 3 and the first two. This one, we now have a 3 that's written there. The first two, we didn't have any number, and when there's no number written, it's understood to be the square root. So here we're now looking for the cubed root. So we're not looking for 4 or 9 or 16 that go into it, because those are perfect squares. So now we're looking for 8, because a cubed root of 8 is equal to 2, so it's a perfect cube. We're looking for 27, because a cubed root of 27 is equal to 3. We're looking for 64, because a cubed root of 64 is 4. So we're looking for perfect cubes now that go into it. And 27 goes into it 5 times. So 135 is equal to 27 times 5. So then from here, I can rewrite this as a cubed root of 27 times 5. Now I'm going to look at them individually. The cubed root of 27 times the cubed root of 5. And the cubed root of 27, as I said, is 3. So it's 3 times the cubed root of 5, because we can't actually take that. So we take out any perfect cube now that's embedded within that number. All right, and here it's a really big 6 that's written next to it. So you notice when we wrote the cubed root, it's the small number that's written inside that little corner. That's called our root that we're taking, our index. So here, when it's written really big like this, it's not the 6 root. This is actually saying -6 times whatever this is. So then from here, we need to then go ahead and remember that this needs to be multiplied to whatever we take out at the end. And now 243 is equal to 81 times 3. So, and 81 I know is a perfect square. So I can then say, well, it's -6 times the square root of 81 times 3. And now I'm going to separate these. It's -6 times the square root of 81 times the square root of 3. And the square root of 81 is 9. So it's -6 times 9, which I know is -54. And I can't take the square root of 3, so it's going to remain on the inside. So it's -54 times the square root of 3. All right, for number 5, if I gave you a fraction 2/3 and I said, well, simplify this fraction as much as possible, that is its most simplest form. There's nothing else that we can do. Well, here, the cubed root of 9. There is no perfect cube that can divide evenly into 9. So this is its simplest form. So you can either just circle the question, rewrite it, but if you just leave it blank and don't do anything to let me know that you understand that is the simplest form, it wouldn't be considered correct, because it would just be considered that you didn't know how to do that one. So make sure you're doing something to say, well, this is the simplest form. There's nothing else we can do. All right, so for this one, once again, you see now we have the big number written, and then we have that little small number. So we're saying -4 times the cubed root. And when we have a cubed or an odd root, well, -2 times -2 times -2 is -8. +2 times +2 times +2 is +8. So whenever we have an odd index, if the number on the inside is negative, that's fine. That's just telling us we're going to pull out the negative. So we'll never leave a negative inside our radical, because we want to simplify as much as possible. So we're going to pull that out with it. So the perfect cube that goes into 24 is 8. 8 times 3 is equal to 24. So I'm going to rewrite this as -4 times the cubed root of -8 times 3. And then from here, I'm going to separate them. Well, -4 times the cubed root of -8 times the cubed root of 3. And I know the cubed root of -8 is -2. And -4 times -2 is a +8. And this I can't simplify or do anything with, so it's just going to remain 8 times the cubed root of 3. So make sure if it's odd and the number on the inside is negative, you must take out that negative with it. Otherwise, you didn't simplify it as much as you possibly can. All right, now for this one, it's the square root of 175 over 15. Well, I know 25 goes into 175 7 times. So I'm going to rewrite this then as I'm going to do just this off to the side and then put it over that 15 at the end. So square root of 175 is 25 times 7. Well, the square root of 25 times the square root of 7. Square root of 25 is 5. So I know that's equal to 5 times the square root of 7. And this is all over top of 15. So these numbers, 5 over 15, if I just gave you as a fraction, we can reduce that or simplify it. So we still do that here. 5 and 15 are both divisible by 5. So I'm going to simplify this fraction, and it now becomes the square root of 7 over 3. All right, so those first 7 questions, you'll be able to use your calculator on your iPad because um, it can't do it for you, but you won't be able to use the Casio calculators that we have. The rest of the tests, so you can. Now, questions 1 through 7, that was simplifying radical. So I was giving you an expression and it's saying write this as simple as you possibly can, whereas these ones were solving for an equation. And you see it's posed to us differently. Even though we're going to see radicals and even though we're going to see that, the question here is saying what number squared is equal to 36? So if I do 2 times 2, well, that's equal to 2 squared, and that's equal to 4. What if I did negative 2 times negative 2? That's equal to negative 2 squared because we're multiplying 2 of them, and that's also equal to 4. So when we have an even power, there's 2 different numbers that we're going to generate. So just like when we learned that x plus 5 is equal to 8, we subtract 5 from both sides because that's the inverse operation. Well, here the inverse of a square is a square root. So I'm going to take the square root of each side. Anytime that we have the same index, which is the root we're taking, and power, they will cancel each other, and we just get that x. But now, since the question was what number squared is equal to 36, well, I know the square root of 36 is 6. However, a positive 6 squared is 36, but so is a negative. So when you're answering these, you must give me both answers for that because a positive and a negative number, when squared or raised to the 4th power or raised to the 6th or 8th or 10th and even power, will always be positive. So since the question's posed differently than just simplifying a radical of square root of 36, the answer must be plus or minus. Whereas for number 9, it's saying x cubed. Well, 2 times 2 times 2 is 2 cubed, and that's equal to 8. But negative 2 times negative 2 times negative 2 is negative 2 cubed, and that's equal to negative 8. So you see when it's an odd power, whatever the sign is of the number we're taking the root of is the sign of our answer. So so in this case, we don't do plus or minus for it. It's whatever that sign is. So here we would take the cubed root of each side because we're raising it to the 3rd power. So we need the power to match our index. They cancel. So x isn't equal to, and the cubed root of 8 is 2. So x isn't equal to 2 because what number raised to the 3rd power is 8? Well, that is 2. And you can think, we learned this before as well. If you remember when we were manipulating our bases, we were rewriting, and when we were like using our exponent laws to divide really large numbers, we were rewriting as 8 as 2 cubed. So this, we can say x cubed is equal to 8. Well, I know 8 it can be written as 2 cubed. So then this should just make sense for you. Well, if this number is being raised to the 3rd power and so is this, since the powers are exactly the same, that means x has to be 2. And if we took the cubed root of each side, I see that the power and the index are going to cancel for both, and x must be equal to 2. All right, so here we look and say, okay, it's being raised to the 2nd power, so I'm going to take the square root. What I do to one side, I have to do to the other. This cancels out and isolates and brings my x out by itself. And that's okay. Well, what is the square root of 121? It's 11. But since it was a even power, I know that a positive and a negative number can generate that because negative 11 squared, a negative times a negative is positive. 11 times 11 is 121. So negative 11 squared is 121, but so is positive 11 squared. So you have to give me both those answers. Here, we say, okay, x cubed is negative 125. So I need to take the cubed root of each side. That's going to isolate and bring out my x. And then the cubed root of negative 125 is negative 5. It's not plus or minus because negative 5 times negative 5 times negative 5 is negative 125, whereas a positive 5 times itself 3 times is positive 125. So you see, when it's a cubed or an odd power, it's not going to always be the same sign because there's going to be that one negative that's left over if it is negative. Where when it's even, we're always going to have equal pairings of the negative. So each of those pairs will turn to positive, which means we'll ultimately end up having a positive number. All right, and then for number 12, for this one here, we're going to go ahead and say, okay, well, let's take the square root of each side. And you'll be able to use your calculator for this one, so I'm not going to go through simplifying this. If you just type this in your calculator, 49 does go into 147 3 times. So this, when we type this in the calculator, it'll be 7 times the square root of 3. But even though now that this is still has a radical in it, you still have to do a plus or minus because the square root of 3 just represents a value, a number 1.7. So it represents an actual like number or decimal if we wanted to convert it to that. So you still have to make sure you write that plus or minus, even though there's that square root left over. For number 13, so for this one, cubed roots, the calculator doesn't do it for you, so you would still have to simplify this on your own. But we're going to take the cubed root of each side to isolate that x. And then when we get this cubed root of 686, we're going to go ahead and have to simplify this. 7 cubed is equal to 343, and 343 goes into 686 twice, so we can rewrite, we can rewrite the cubed root of 686 as the cubed root of 343 times 2, and the cubed root of 343 is 7, so x is then equal to 7 times the cubed root. I can't take the cubed root of 2, so that stays in. So 7 times the cubed root of 2. For number 14, I was just hoping that you guys can make some connections of what we learned before, and that regardless of what type of question we have when we're solving an equation, we need to simplify it as much as we can. Now, we're only learning how to do the basic ones of these, and when you guys learn this next year, there will be something else that you have to do, but for right now, we're just learning the basic ones. So we're never going to have an x squared and an x be part of the problem that is part of our standard. You might have that in your exceeding, which is seeing if you're above grade level or not. So just like if I gave you this without this here, you would have to simplify first, which means multiply and combine like terms. So that's what we're going to do here, because I know parentheses means to multiply. So I'm going to distribute this -4 in. I'm just going to zoom out a little bit, so that way it can be a little bit more space. So 2x squared minus 12 is equal to 4x plus 56. Well, -4 times x is minus 4x, and -4 times 1 is minus 4. Here, positive 4x and minus 4x, they're on the same side, so we just combine them, and 4 minus 4 is 0. And that's what I mean. I'm never going to give you a question that counts towards your standard that x squared and x will both be present. And 56 minus 4 is 52. So 2x squared minus 12 is equal to 52. Now, if I just gave you 2x minus 12 is equal to 52, how would you solve this? It's the same steps that you would be doing. So we have our PEMDAS. It's the same steps that we were doing for this, because you see, if I add the square there, like the actual problem, the exponent comes when we're unpacking our box, it's coming after the addition that we need to do and after the division that we need to do. So we need to do those other steps as if it was just a linear question that we learned. So I'm going to add the 12 to both sides. So now I get 2x squared is equal to 64. And then I'm going to isolate the x squared. So I'm going to divide each side by 2 to get rid of that multiplication, since it comes before our exponent. And now I get x squared is equal to 32. And now once I isolate that variable of x squared, now I can take the square root. So x is equal to, and since it's a even power, it's going to be plus or minus. Square root of 32 is not a perfect square, but you're allowed to use your calculator for this. And we type it into your calculator, it's going to give you 4 times the square root of 2. So I'm not going to go through and simplifying this one, because since you're allowed to use a calculator for this section, it's just doing it for you. All right, so this one is x is equal to plus or minus 4 times the square root of 2. All right, and then for this one here, just like if I gave you x plus 64 is equal to 0, we need to isolate that x first. And when you have just an x raised to a power and no other x's there, you just treat it like it's linear, and then you just take the root of that power. So I'm going to subtract 64 from both sides. So x cubed is equal to -64. And now I'm just going to go ahead and take the cubed root of each side. That's going to cancel out that x cubed. So x is an equal to, and the cubed root of -64 is -4. So that would then give us our final answer. And for this one here, since x squared is equal to -49, and we talked about this, I know that square root of 49 is 7, but 7 times 7 is equal to 49, but -7 times -7, is also equal to 49. So there's no number that I can multiply by itself twice to give me a -49. So we talked about this in class. You will learn that this is actually something you will be able to do like in a year or two, and it generates a complex number, which is an imaginary number. So here we say no real number or no real solution. because there is a solution for this that you're going to learn. So I don't want you to say no solution, period, because then in the future you're like, oh, Mr. Spellman said that this can't be done, but it can. It's just not part of the number systems that we're focusing on right now. So if you said no real number or no real solution, that would be acceptable, because there's no number that we know of yet that when we multiply itself twice gives me negative 49. And then the last one here is, it says this sugar cube box is a perfect cube. Its volume is 1,728 cubic centimeters. Sugar cubes are 1 by 1 by 1. Well, how many cubes can fit along the length of the box? Well, volume, we know for a cube, is equal to the side raised to the third power. So if our volume is 1,728, that means to figure out what each side length is, or how many can fit in, well, we would say, well, s cubed is equal to 1,728. So then we would need to take the cubed root of each side, and that means s is equal to 12. And since each cube is 1 by 1 by 1, and we know that the side of the box is 12 centimeters based on the volume that they gave us, then that means we can fit one cube. Each cube's 1 centimeters, so we can fit 12 cubes. So we can fit 12 cubes along this side of the box. We can fit 12 cubes. So since it's a perfect cube, the width of the box is going to be the same as well, because that's the dimensions of each side. So we can fit 12 cubes in the width, and we can fit 12 cubes on the height. And then from here it says how much cardboard is used to make the box. Well, that's the outside. So what we need to do then is we need to find the area of one of the sides of the box. An area is equal to our s squared, and we know our side is 12. So our area is equal to 12 squared, which is equal to 144. So the area of one side of the box is 144 centimeters squared. And here we have 6 different sides. We have this left side. We would have the exact same side of it on the right, so that's 2. We have the top, and then we would have the bottom. We have the front, and we would have the back. So there's 6 perfect sides, or 6 sides that are all perfect squares. So we would then take that 144 and times it by 6, and 144 times 6 is then equal to 864. So we would need 864 centimeters squared total in order to make the box to perfectly fit those. All right, that is it. Tomorrow we'll have a little mock test, and then I'm going to make sure it's not the full class so we can go over questions at the end.